Okay, so why do we use datum reference frames to measure part features? Um, well, essentially, it gives you a much better check of the parts. Okay, we can argue that if you weren't using datums and GD&T and you're just dimensioning these holes using plus or minus tolerances, that you really don't know where you're at. You really don't know what your parts are, and you really don't know if your parts are going to fit. And the reason why I say that is here is how we're checking parts with GD&T using a datum reference frame. We have a datum plane B, we have a datum plane C. We have all of these imperfect edges on these surfaces that of the part, these datum features of the part. Okay, and what we want to know is, will these holes be in the correct position to be able to fit in our assembly? Okay, so that's why we use GD&T, because if we're just coming over here and just measuring this hole here from the edge of the part, we could be picking up this little crook here, this little hump here. Um, it does not give us an accurate reading. Okay, it doesn't tell us where this hole is relative to a simulated datum over here. So essentially we don't really even know if our parts are going to fit. Okay, so this is why we use datums, because you can't really check a part without them. I mean, check the part faithfully. Okay, in a lot of cases, you would be able to get close enough, but we're talking about making interchangeable parts here that fit in assemblies, and these interchangeable parts can be made anywhere in the world, in which case we really need to use GD&T so we know our parts are going to fit at the next level assembly. I could spend all day talking about this point, but it is very, very, very important. Let's talk about degrees of freedom for a little bit. Yeah, this gets into the tool design aspect, and this is kind of what we do when we define datums. Okay, so we have 6 degrees of freedom. There's 3 translational and 3 rotational degrees of freedom. Okay, so if I was to set a part down in this datum plane without these other 2 datum planes, the part could slide across that datum plane, and therefore that's a translational degree of freedom. Okay, so that's a movement. And then rotational, these would be the rotational degrees of freedom. That's rotation about the axis. So what datum features actually do is they constrain degrees of freedom. So when I think about this part, first of all, if I only had the 1 degree of freedom constrained, for instance, I could put my part down on this plate here, and then it would be able to rotate. It wouldn't be able to rotate about this axis because I got it constrained to this plane. Won't be able to rotate about this axis because I got it constrained to this plane, but it could rotate about this axis too. So then when I put this datum plane in here, I've constrained the translational degree of freedom. And when I put the third one in, I've locked the whole part all down. So I've constrained the degrees of freedom. So that's what um, establishing a reference frame does for you. And really, if you were a tool designer, that's how you would gauge the part. That's how you would hold the part for manufacturing. That's how you would inspect the part later. And we're going to talk about gauges for inspecting parts later. Um, so let's talk about datum identification. Okay, datum feature symbols. Really, we place datum identification on a drawing by using a square with the datum letter in it, and then a little leader off of it, a little straight leader attached to a filled-in triangle. So a square rectangular containing 1 or more letters connected by a short leader to a triangle. That's how we identify datum surfaces on a drawing. Now, datums can be either surfaces or they can be features of size. Okay, up here we're talking about how to apply to surfaces. We come off with an extension, and then we apply the datum to that extension line. Or we can apply the datum directly to the object of the part. Or in this case, we put it here with a dot that defines this surface facing us as datum E. And then from that leader, we put a datum with a triangle off of it. Here's another way to do it. And we can put that on either side of this extension line. That's okay. And the other way to do it is we put a perpendicularity tolerance on this surface here, and then we defined it as a datum. Now when we're applying it to a feature of size here, there's several ways to do it, but this is one where we take the datum triangle and we place it directly in line with the dimension line. Okay, and that tells me that this feature of size, this diameter, this hole, 0.250 plus or minus 2 thousandths, is datum J. Only applied to physical features. We don't apply these to center lines, like I said, and it's not required when datum targets are applied. We're going to talk about datum targets here in a bit. Okay, so datum feature symbols on flat surfaces. Here's how we apply those here. Flat surfaces are commonly used as datum features. They establish datum planes, and datum features may be of other shapes, but here's how it is. We can apply the datums like this, or like this, or like this, or like this. So high points on imperfect surfaces contacted by simulators to establish the simulated datum location. So in this case, we have a tool set up where we have a datum simulator for A, we have a datum simulator for the B surface, that's this plate back here, and we have a datum simulator for the C surface. Okay, so we can take this piece and we put this in here and it will simulate all three of our datums. Okay, so here's how we would apply a datum feature symbol on a cylindrical feature. This would be the model representation. We pointed to surface here. And in which case here, what we've got here is we're looking at a drawing orthographic view here. We have the datum triangle in line with the dimension line, in which case these are both features of size datums. So cylindrical features are commonly used as datum features. They establish a datum axis. So when you establish a datum on a feature of size, what you're doing is creating an axis through that part. And then, of course, other features may be used, but the actual mating envelope establishes the datum axis when referencing at RFS. And we're going to talk about that point in a minute. Let's talk about target symbols. So far we've applied datums with surfaces. Now there's another way you can apply datums to a drawing, and that's through target points. Now these target points are essentially listed like a circle with a leader, and then there's a horizontal line through there, and then this is the number of datum points. So datum A would be a target point for A1, and this could either be a point like we're seeing here, or this could be an area. Okay, that's a square area, or that could be a round area, and we have the shape and size of the area up here in the upper half of this. And then in this case here we have the identification A1, but we have two dimensions that define that. So the bottom half identifies the datum target with a letter and a number, that's A1 here, and the top half is empty except when you're specifying a datum target area or size. The leader has no terminating arrowhead or dot. Okay, so datum targets may be a point, represented like this, a line represented with a phantom line, and then also an area. Now when you're identifying an area, you always use the phantom line around the perimeter of the area. Okay, that's very important. Datum feature symbols typically not shown with targets, so you don't really show the A in a rectangle with a triangle. You don't do that when you're using datum targets to establish your datums. Okay, so let's talk about target points first. I guess we're running a little bit long. I'm going to pick up target points in the next movie. Thank you.